Good evening, all. I'm Pramod Gal, TA of this course. I'm going to take a problem solving session 6 on the course Chemical Reaction Engineering 1, week 6, on reactor design for single reaction. The course tutor is Professor Vishwata Mandal, Chemical Engineering Department, IIT Guwahati. So, last class we studied for reactor design, means performance equation for the ideal reactors, batch CST and PFR. So for this today's sessions, this is a brief recap. Size comparison of single and multiple reactors. In size comparison, multiple reactor, then recycle and autocatalytical reactor. So based on that, I'm going to take problems. Uh, so starting from the MCQ one, question one. Choose the correct options. Here is a option given. Each batch reactor are used in the laboratories for the calorimetric titration. So the batch reactor are not used for the calorimetric reaction. So this is first one. The steady state flow reactor is mostly widely used because it needs a little supporting equipment. Basically, the steady state flow reactor are best suited for the fast reaction, but their supporting equipment needs are significant. This also. And batch reactor are ideal for the fast reactions also. So in steel industry, semi-batch reactor are used for the large open earth furnace. So semi-batch reactor offer a good control on the reaction speed and so are used in calorimetric titrations and large furnace. Option D is question two. Autocatalytic reaction are the ones in which option are given. One of the product Python, the catalyst. B, there is no catalyst employed. C, only one reactant is involved. And D, one of the product catalyze the reaction. In autocatalytic reaction, the reactant is catalyzed by the product. And one of the product is also the reactants. So option D is match. Question 3. The sequence in which the three CSTRs of volume 5, 10 and 50 cubic centimeter cube will be connected in series to obtain the maximum production in the second order irreversible reaction. Here is a second order irreversible given and volume given. So here is the sequence. We have to select the sequence. So for the best performance of CSTRs, so En here is in order n greater than 1, n less than 1, and n is equal to 1. Here n is the order of reactions. So n is greater than 1, the smallest reactor should come first. When n less than 1, largest reactor should come first. Right. When n is equal to 1, equal size reactor are this. Equal size reactor this. So here second order reaction means n is greater means smallest reactor should be come first. Now check the options. Here is a ascending order 5, 10, 15. So option B is match. Mumpi, the question number 4. For a tubular reactor with a space-time R and resident time theta, the following statement holds. Tau and theta always equals option A, tau is equal to theta. When the fluid density change in the reactors, so tau equal to theta means T resident times. For isothermal tubular reactor in which density of process fluid is constant. And tau is equal to theta for non-isothermal reaction. So for the system of constant density, the performance equations are identical. So tau for the plug flow is equivalent to the T. The T for the batch reactors. The options is correct. Question 5. In order to achieve the same conversion under identical reaction conditions, the feed flow rate of non-autocatalytic reactor of positive order. The volume of ideal CSTR is. The option given. So for any particular duty and all the positive reaction, the order of CSTR reactor always larger than the plug flow reactors. The option is correct. Question 6. An elementary liquid phase decomposition reaction A gives B, the carried constant, is to be carried out in CSTR. The design equation is. So here is a gives B the elementary reactions. So RA, the rate equations for these reactions A, C, A, right? So here is liquid phase means density constants epsilon A is equal to 0. So right, so performance equation for CSTR this is the first order reactions. So K tau equal to XA 1 minus XA. So option is the conversion for the first order reaction. Liquid phase reaction A gives B in CSTR is 50%. If another CST or of the same volume is connected in series, then the percentage conversion at exists of the second reactor. Right. Here is the first order reactions and the conversion given. So we have to calculate the exist conversions. Here case 1. Right. This is CSTR inlet outlet C0 CA1. Right. So here X is given 0.5. Right. So CA1 equal to CA0 1 minus XA. Right. So put there this value, you get 0.5 CA0 CA1. Now case 2. another same value is connected in series. This first. CA not CA1, CA2, right? So same sorry, 0.5, 0.5 means CA2 equal to CA1, 1 minus X. Okay. So 0.5 CA1. CA1 equal to 0.5. So 0.25 CA0. CA2. So percentage conversion at the exist of the uh, second reactors. So XA overall equal to CA0 plus CA2 plus CA0. So put the value CA2 into 0.25 CA0 equal to 0.75 means 75%. Option B is mass. So there is another method to solve these ones using this one. And 1 pi or minus xn equal to 1 plus k tau n, right? So using this formula you can calculate the exist convergence means xn. Question at an isothermal liquid phase zero order reactions, A gives B zero order. K is equal to 0.5 mole per meter cube per second. It's carried out in a batch reactor. The initial concentration of A is 2 mole per meter cube. At a 3 second from the start of the reaction, the concentration of A in mole per meter cube. So here batch reactors. So initial K given, initial mole given, T given. So we have to calculate. We have to calculate the outlet concentrations, right? So this is liquid phase means constant density, zero order. The performance equation Qt by Ca naught is Ca naught is Ca by Ca naught. This get cancels. So Kt equal to Ca. So Ca is equal to Ca naught minus Kt. Ca naught given to K 0.5 and K 3. It's 0.5 mole meter cube. Let's see. So moving to the next questions. 9. Here is a statement given. A liquid phase reaction A gives B is conducted isothermally in a C-star having a resident times. Temperature constant isothermal means having resident times of 2 seconds. The inlet concentration of species A is 2 mole per liter and outlet concentration is 1 mole. The rate law for the reaction is given where K is equal to 5 mole per liter per second. The value of K in moles per liters. So we have to calculate the key, this one. So here initial C naught, CA, then so here is a precedent time tau given, right? The performance equation is a design equation for the CSTR C naught equal to XA RE, right? So tau equal to C naught, right, into XA into, sorry, divided by, right. So tau is equal to C naught into XA into RA. Put this value A plus CA small a, right? So this value given, CA given, this ones. Now we have to calculate the XA. So XA is equal to CA naught at CA by equal to 0.5. So put the value CA naught given, XA given, tau 2 seconds. Here is we have to calculate this key, capital K. So put the value, we will get K is equal to 9 mole per liter. Option B is right. Now, based on the same statements, the question 10, if the same reaction is conducted in a series of two CSTRs with precedent times 1 seconds and 2 seconds, then the inlet concentration of A in mole per liters required to attain the outlet concentration of EA. Right. So, you have to calculate the inlet concentrations. So, here is a two CSTR in series. So, CA0, CA1, CA2. Right. So, here is K given small and capital K we calculated just now 9 mole per liter, right? K is equal to find and Ca means final Ca not, sorry, Ca2 equal to 1, right? So now is equal to Ca not Ca1 performance equals for CSTR Ra Ca1 naturally Ca1 minus Ca2 equal to 1, right? So here precedent time for the secondary reactor find 2 Ca1 Ca2 given 1 mole into 5 1 this rate equations 9 plus 1, right? You will get the C1 equal to 1.1 mole per liter. Right. Now coming to the this part. So here reset time 1 second. C naught here is the 1.1, then 1.1 divided by 9 plus 1.1. So we will get C naught equal to 1.64 mole per liter. Option C is correct. So moving to the next questions. Here is a statement for question number 11 and question number 12. In an aqueous solution, the reaction P gives Q occurs under the isothermal condition following first order kinetics. The feed rate is 500 centimeter cube per minute, and the concentration of P in the feed is 1.5 into 10 to the power minus 4 mole per centimeter cube. The reaction carried out in 5 liters CSTR at steady state 60% conversion observed. The rate constant in minute. Here feed rate given and first order reaction CSTR. The perform equation for the first order reaction A naught CA six A minus 6. 1 minute. Right. So here feed rate given, volume also given. So we can calculate the tau is equal to volume. Correct. So here is a 5 and volumetric flow 500 centimeter cube to convert into the liter per minute. So it's a 0.5. Right, liter per minute. So it's a 10 minute. So put this in equation. This one K into 10 and conversion 60. 0.6 and 0.4. Right. So K is equal to 0.15 minute inverse. Option B. Now question number 12. The 5 liter CSTR is replaced by 5 CSTR in series. If the capacity of each new CSTR is 1 liter, then the overall conversion in percentage. So as you know, C naught divided by C n equal to 1 xn equal to 1 plus k tau I is to the power n. Here is a number of reactors. K rate constant is tau resident times. Here is the initial concentration and final. So here tau I V by V naught. we reserve 1 liters and we not given 500 centimeter cube uh, in liter per minute 0.5. It's a 2 minute. Right. So 1 by 1 minus 18 equal to 1 plus k 1. Yeah. Right. So we calculated just now 0.15 minute inverse and you need the 5 reactors. To put in this equation and calculate the xn. So xn is equal to 0.73, 73%. Option C is correct. So moving to the question number 13. So here is a statement for the question number 13 and 14. The statement is the first order liquid phase reactions A gives P is conducted isothermally in plug flow reactor PFR of 5 liter volume. The inlet volumetric flow rate is 1 liter per minute and inlet concentration of A is 2 mole per liter. Right. If exit concentration A is zero point 0.5 moles per liter, then rate constant in the minute inverse. So here volume given of PFR, then in the volumetric flow rate 1 liter V naught. Here is the inlet concentration C naught. Here the exit concentration V given. And first order liquid phase reactions. The performance equation for first order reaction for a PFR K tau ln C naught by Ca. So here Ca naught given, Ca given, K we have to calculate tau. To calculate the tau, V by V naught. V given, V naught given. So it's a 5 by 1 equal to 5 minute. Put it in this equation. So we will get a K equal to 0.278 in this one. Option this one. Now question number 14. The plug flow reactor is replaced by 3 mixed flow reactor in series, each of 2 liters volume. The exact conversion of E. So this is how to use the same concept as the previously questions. 1 by 1 minus x n equal to 1 plus k tau I n. Here is a integer 3, volume 2, and k calculated at 0.278 minute inverse. Right. So x n equal to 0.7346 and 73.746. Question number 15. A homogeneous reaction argues P occurs in a batch reaction. The conversion of the reactant R is 67% after a 10 minute and 80% after 20 minutes. The rate equation for this reaction. So I have to calculate the rate equation. So as you know, for the nth order reaction, Ca 1 minus n equal to Ca naught equal to n minus 1 Et. Right? For the nth order k is equal to Cn. After integrating this Ca by dt, after integrating you will get this expressions. Now this Ca by Cn naught 1 minus n equal to Cn naught 1 minus n in minus 1 dt. Right. So we can write down these terms 1 minus xa, right, n minus 1 dt, right. Now t is equal to 1 minus equation 1 xa 1 minus n by 1 divided by n minus 1 a naught 1 minus n into k. This is equation 2, right. Now for t is equal to 10 minute and conversion 0.67 and t is equal to 20 minute xa is equal to 0.8. So based on the equation 2, take a ratio T2 means T20 by T20 by T10, okay, 1 minus 0.8 1 minus n 1 minus n minus 1 into n minus 1 a naught raised to the 1 n minus 1 into k. This get cancels distance. So here put value T2 25 k equal to 2. So find 2 1 minus n 0.33 1 minus n 1, right. So now try a different value for n like 1 2 3. So try n is equal to true, try n is equal to 2. You can try for 1 2 and 3 also. So for n is equal to 2 is 2 0.2 1 minus 2 1 0.33 1 by 2 minus 1, right. So you solve, you will get. So LSS is equal to RSS. So therefore n is equal to, so R equal to is CA here, right. Sorry, CR. Check the options. Option B is moving to the question number 16. A reaction A gives B is to be conducted in a 2 CSTR in series. The steady state conversion desired is except the reaction rate as a function of conversion is given by R is equal to minus 1 by 1 plus 6. If the feed contains no B, then conversion in the first reactor that minimize the total value of two reactor. So X1 X a feed between x1, x1 means we have to calculate the relations. So here are the two CSTR series. XAF, XA1, is V1, V2. Okay. The design equation for CSTR V equal to XAF plus XAI. RE. For the case 1 and CSTR 1, so V1 by if not equal to XA1 A naught minus RA, right? So RA here given, put it in this equation. So here is a J0. Initial concentration is, sorry, initial energy is 0. So XA1 minus 1 by 1 plus XA, right? So V1 by F naught equal to XA1 1 plus XA, right? Now CSTR2 V2 by Fa naught equal to XA2 minus XA1 by minus RA. So XAF minus XA1 plus 1 1 plus XAF, right? So V2 A naught equal to XAF minus XA1 1 plus XAF, right? So now total value P divided by F equal to V1 by plus V2. Put the value in these equations. So V is equal to Fa naught XA1 here plus XAF here XA1 X. Now conversion is the first reactor that minimize the total value of the reactor. It means that d by dx1 equal to v by equal to 0. And this one's twice x1 plus this constant 0 and x. Right. So twice x1 equal to xa. So xa1 equal to xaf. Take the options. So C is. So moving to the question number 17, and this is last one. First order liquid phase reaction is carried out isothermally at a steady state in CSTR and 90% conversion is attained. with the same inlet condition and same overall conversion if CSTR is replaced by the two smaller and identical isothermal CSTR in series. The reduction in total volume to the nearest integer is. So here first order liquid phase reactor carried out in CSTR. So here X conversion given. So at same inlet condition and same overall conversion, if the CSTR is replaced by two smaller identical CSTR, then how to calculate the percentage reduction in total value. So calculate this. So as you know, C mod by Cn to 1 by 1 minus Xn to 1 plus K. Right. Now going back case 1, here n is equal to 1 for this one and Xa is equal to 0.9. Right. This is equation 1. So 1 by delta x1. Here is a n is equal to 1. 1 plus K y 1. Put the value in this equation. 1 plus K tau I. So tau can write down V by V naught. V value here volumetric for volumetric flow rate. So K equal to V1 by volumetric flow rate equal to the 9. So V1 equal to 9 by V naught. Now case 2 means CSTR replaced by the two smaller identical isothermal CSTR in series. Based on the equation 1 minus x2 equal to 1 plus t2 and tau 2 here. And x is 0.9. So 1 plus t2 equal to is 3.1623. Right. A 2 tau 2 equal to 2.1623. Right. So tau 2 V2 by V naught. So V2 equal to 2.1623 into V naught by K. Right here, right now only K. Right. Now total volume for the 2 CSTR. So V2 equal to twice into 2.1623. Means 4.3245 V naught by K. Right. Now I have to calculate percentage reduction in the total value. So to calculate the percentage reduction in the value, to V1 by V2 by V, right, into 100. So 19 V naught by K 4.3245 V naught by K and 9 V naught by K. Thank you. So 51.95%. The percentage reduction is 51.95%. So I cover all the questions so based on the six chapters, means reactor design for the single reactions. So thank you all. We will meet on next Friday on next chapters. So reactor design for the multiple reactors. Thank you.